Hi everyone. In this video, I am going to explain the Nyquist count and closed loop stability. This topic can look difficult at first because there are complex planes, plots, and equations, but the main idea is not too hard. Nyquist method help us check whether a closed loop system is stable or unstable. Instead of solving difficult equations, we use a graph. That graph is called a Nyquist plot. By the end of this video, you will understand what the Nyquist counter is, how it becomes a Nyquist plot, why the point minus 1 plus j0 is important, and how we use the Nyquist formulas to check stability. First, let's understand why this topic is important. In control systems, stability is very important. Uh, Stable systems work properly. Its output stays under control, but unstable system can oscillate, increase without limit, or even fail. For examples, think about an aircraft autopilot system. If the system is unstable, the aircraft may not move smoothly. It may keep oscillating. Another example is a chemical plant. Imagine if the control system is unstable, temperature or pressure can become dangerous. Normally, to check stability, we look at the closed loop faults. If all closed loop faults are in the left half plane, the system is stable. If any faults in the right half plane, system is unstable. But finding closed loop fault can be difficult, especially when the equation is large. This is why Nyquist method is useful. It's allow us to check stability using the open loop transfer function and a graph. Sorry. Now let's quickly remember the basic stability idea. In the S-plane, the left side is called the left half plane. The right side is called the right half plane. For stability, all closed loop poles should be in the left half plane. You can see this green color area. If any closed loop pole is in the right half plane, the system becomes unstable. That area marked as red color. The closed loop characteristic equation is 1 plus GSHS equals 0. The root of this equation are the closed loop folds. So if we know how many roots are in the right half plane, we can decide whether the system is stable or unstable. Nyquist method help us finding without solving the full equation directly. What is the Nyquist counter? A Nyquist counter is a closed loop path drawn in the S-plane. This is drawn around the right half plane. We choose the right half plane because that is the unstable region. The counter has two main parts. The first part is the imaginary axis. This is the line where s is equal to j omega. When we use s equal j omega, we are looking at the frequency response of the system. So along this part, we evaluate g of j omega, h of j omega. The second part is a very large semicircle in the right half plane. This semicircle close the path. So simplify, the Nyquist count is like an inspection path around the unstable region. Now let's see how to construct it. First draw the S-plane, then mark the right half plane. After that, draw a path along the imaginary axis. Then close the path using a large semicircle through the right half plane. This gives us a closed loop counter. One important point is this: if there is a pole on the imaginary axis, we should not pass directly through it. Instead, we draw a small curve around it. This is called an indentation. After drawing the counter, we pass it through the open loop transfer function g of s, h of s. That gives us Nyquist plot. Now let's understand mapping. The Nyquist counter is drawn in the S plane, but Nyquist plot is drawn in the GS plane. To get the Nyquist plot, we take every point on the counter and substitute into g of s, h of s. So the transfer functions change the counter into new curve. That new curve is called the Nyquist plot. A simple way to remember this: Nyquist counter is the input part. G of s, h of s is like a machine. Nyquist plot is the output part. After getting the Nyquist plot, we check whether it encircles a special point. That special point is -1 plus j0. Now, now let's talk about the critical point. The closed loop characteristic equation is 1 plus GSHX equals 0. If we rearrange it, G of S H of S equals minus 0, minus 1, sorry. Rearranges gives G of S H of S equal minus 1. In the GH plane, minus 1 is the point minus 1 comma 0. So this point is called the critical point. This point is very important in Nyquist stability. It represents gain equal to 1 and phase shift equal to minus 180 degrees. At this condition, feedback can make the system unstable. So in the Nyquist method, we check how the Nyquist plot move around this point. If the point encircles this point, we count the encirclements. Now we use the Nyquist stability formula. The formula is n equal n plus p. Here Z means the number of closed loop poles in the right half plane. N means the number of encirclements around the point minus 1, comma 0. P means the number of open loop poles in the right half plane. For the closed loop system to stable, Z must be 0. That means there should be no closed loop poles in the right half plane. So the final idea is simple. First find P, second find N, third calculate Z. If Z is 0, the system is stable. If Z is not 0, the system is unstable. In the next flow slides, I have had a simple Nyquist example. You can see the example clearly in the presentation that I upload with this video. I explain it step by step, so please follow each step carefully. And final conclusion of this example, we can get idea. This is a stable system. So end of this presentation. To summarize, the Nyquist counter is a path drawn around the unstable region in S plane. When we pass this counter through g of s, h of s, we get the Nyquist plot. Then we take the Nyquist plot around the critical point minus 1 plus j 0. Finally, we use the formula z equal n plus p. If z equals 0, the closed loop system is stable. If z is greater than 0, the system is unstable. So Nyquist method is useful because they help us check closed loop system stability using a graph without solving difficult equations. So thank you.